Next proof. We are given that OK bisects MOT and it bisects angle MKT. We probably have alarms going off in our head of like, hey, I know what bisect means. It means that it makes them equal to each other. Okay, awesome. Let's go ahead and go down that garden path. Get started on our labyrinth. Okay, well that gives me that angle 1 is equal to angle 2 and angle 3 is equal to angle 4. And they don't rely upon each other in order to be true. They just relied upon the given in order to be true. They had to be said that it was bisected in order for that to be true. So you can put them in the same statement because they're the same reason. Definition of bisect. I'm going to show myself what I've got going on. I've got two angles. It could be either angle, angle, side, or angle, side, angle. Hopefully you're like, duh, reflexive property, easy, angle, side, angle. Well, you're right, student. It is easy. You've got this. Is that empty? Nope. That's okay. That's a side. These are two angles. All right, and now I've got that so now I have that those two triangles are equal, which I definitely want to prove. And that is OKT is congruent to triangle OKM. And that's because we had shown angle, side, angle. I'm going to take a step back and look at my proof statement. My proof statement says, I want you to prove that MK is equal to TK. Well, I have just proven that those two triangles are equal, which means all of those pieces within there are equal to each other now. Now that I've said that they're equal, that the triangles are equal, right? I did not know that those pieces were equal until I proved that the triangles were equal. And then after that, you walked into this room in your labyrinth where there's a million doors, right? And there's six doors. And you can go out any of those 6 doors to where you need it to go to, okay? Saying MK equals TK is just one more step from here. And again, that reason is CPCTC. Drop the mic. Okay. We are given that AD and BE bisect each other. Okay, it means it splits it into 2 equal pieces for both of them. And then we want to prove that E and B are equal. Okay, well, if we want to prove that those small pieces are equal, we're probably going to want to prove that these triangles are equal. And in order to do that, I need to start addressing some of the things that I see in this diagram. Since I know that they bisect each other, I'm going to start then talking about all of those pieces being equal. So I'm going to say that AM is equal to DM and EM is equal to BM. A is equal to DM. Again, I can put them in the same statement, that, and then BM is equal to EM. Definition of bisect. I'm going to go mark it in my diagram because it's like a little checklist for me. It's like, yes, I did that. And then now I know I want to prove those two triangles are equal. I see an X. I'm going to talk about vertical angles. I'm feeling a little lazy. I'm going to call it angle 1 and 2. And then, so I don't have to talk about 3 angles. I'm going to say that they're equal. Because vertical angles are equal. Now I can say that those triangles are equal. AME equals triangle DMB. Because of side, angle, side. But now that's not my final step. That's not my final stop in this proof. My final stop in this proof is to say, hey, say that angles E and B are equal to each other. Now that we've proven that those guys are equal, which they're corresponding parts of these now proven congruent triangles. So I can say that those guys are equal because of CPCTC, E and B. I always wonder when I do that if it gives you guys like seasickness if I'm moving around so much with being zoomed in. Sorry if it does. Last page, we've got 2 sentences that we want us to prove. So in sentences, you have a problem where we're asking you to prove something. The first part of that sentence is your given, and the second part of that sentence tends to be your proof. So if we're looking at here, it says if this, then that. The if part of the statement is your given, the then part is your proof. If we are given that a quadrilateral is a parallelogram, so quadrilateral just means that it has 4 sides, and then we're given that it is a parallelogram, which means opposite sides are parallel. That is the only definition of a parallelogram. Everything else that we know about parallelograms are properties of parallelograms. Once we have that it is a parallelogram, then we can prove that both pairs of opposite sides are congruent. So we do know that parallelograms have opposite sides that are congruent, but you can in fact prove that as a property of a parallelogram. I'm first going to draw a diagram that is something that looks like a parallelogram. I'll put it over here just to kind of mix things up. And I'm going to call it A, B, C, D. And we're given that as a parallelogram. So first step is my given. A, B, C, D. We don't have like parallelogram symbols. And that's because the only reason why we use symbols, not the only reason, but like the big reason why we use symbols for triangles versus angles is because they both have 3 letters. And so you're telling me which one it is. Is it a triangle or is it an angle? So here it's just the 4 letters and you're telling me it's a quadrilateral. It's something with 4 vertices. So A, B, C, D is a parallelogram. Ooh, sorry. I'm getting a hole in my stylus. Okay, so if I know that it's a parallelogram, then I know that opposite sides are parallel. I'm going to go ahead and label that here. AB is parallel to CD, and I know that AD is parallel to CB. And that's your definition of a parallelogram. I'm asking you to prove this in a set of notes that's talking about proving triangles to be congruent. And we have not drawn in any triangles here yet, but we do know that parallelograms consist of triangles, right? So I'm going to go in here and add in any triangle. There's no specific measurements or specific diagram for things like this because it's showing you that this statement is true for any parallelogram. It doesn't matter what parallelogram you drew and what you called it, because no matter what, even if I take these same steps and my parallelogram looks way different than your parallelogram, the statements will still be true no matter what. So what we're doing is we're proving these statements to be true in any possible situation, in any possible circumstance. This will always be true. It doesn't matter what you're drawing. You could draw a really crazy looking parallelogram or you could draw a square, right? So it doesn't matter as long as your proof is correct. You've now proven that all of this is true no matter what.